Oh, yay. Okay, so we're going to start with number 4. And I got it pulled up here, so let's see what we got. It says a firecracker in a coconut. Ooh. Blows the coconut into 3 pieces. 2 pieces of equal mass fly off south and west. Is this our homework?
That was the last one.
That's the last one, isn't it? So Mr. Shelton pulled up the wrong homework. I thought we had done that one. I remember the blowing up coconut. So we want this one. Rotational dynamics. Yeah, that's right. Yay. I mean, you might not say yay, but I'm so happy to have found the right one. Okay. So I have a picture of a box, and it says, in what magnitude force provides 9 Newton meters of net torque about the axle? Okay, so these kinds of box questions like this are, if they show up on the multiple choice. And questions like this have shown up on the multiple choice. So to set these problems up, don't fret too hard about them. First, I've got a force here, and they tell me it is an unknown amount of force, but they tell me the whole thing is a 10 centimeter box. And I believe they have established a pivot point in the bottom left-hand corner. So that's supposed to be the axle. And there's a force here too. So, and they say these 2 forces are the same, so the net force is 0. And it says, what magnitude force provides 9 Newton meters of net torque about the axle? So the first thing I want to point out is that this force provides no torque about the axle. Does everybody see that that has to be true? It's the angle. The angle makes that true. So the only force that actually provides a torque is this one. And based on the fact that it is perpendicular to a torque arm that lies along this plane, I can assume then that that torque could be written as 0.1 for the torque arm length times F, my unknown, times sine of 90 degrees. Any questions about that? All right. They say that the net torque has to equal, in my question, which might be different than yours, my question is 9 meter newtons of torque, although they want you to type it as Newton meters, apparently. Never heard that, but this book is always like that. So 0.1 times F equals 9, so the force has to be 9 newtons. That's it. Questions about that? If I were giving this on a test, I would want you to be able to do something slightly different than this. So just as a kind of a how would this look if it were an FRQ that I was writing? And an FRQ that I'm writing would have kind of like this look to it. So you'd have like a box that's receiving a force here. And it can still say 10 centimeters. But I'd say like the box has a mass of 10 kilograms. And it's a uniform box. That would mean that the box would have a weight acting here. And my question would be, how much force would be necessary for the box to begin to lift the bottom off of the ground? So for this point to come off the ground. It's almost the exact same question as what you just did, but with 2 distinct differences. First, this is the torque arm for the weight, which since you have a 10 kilogram box, you know that this is 100 newtons. And you also know that this is 45 degrees. So you have everything you need to figure out the size of that torque. And you would need this torque arm and this force to balance that. You would need to provide at least the necessary torque so that the net torque was 0, so that anything more than that would cause the box to tip. This is a more reasonable AP level question. And I want you to be aware that that question and this question share the same kind of, material, but this one feels harder. It really isn't. It just feels harder. So you should try that. And you should also expect that it's going to take more force than the weight of the box. Less force than the weight of the box. Because its torque arm is twice as big. So it doesn't take as much weight. It doesn't take as much force. I'd give it a shot, just get an idea. Okay. The next question was number 5. So number 5. All right, so I have something kind of similar. It says, well, I don't have the whole question. It just says what is the torque about the axle? So I think they're referring to this picture. And the picture shows a circle with 4 centimeter diameter and a 20 Newton force here and a 30 Newton force here. The short answer should be that I do one of these it's got a torque with a 30 Newton force and one with a 20 Newton force. The net force difference though is just 10 Newtons. You can find some shortcuts about here. The radii are the same for both. I'm going to do it the long way because I think there's some people in the room who need to see it done the long way, but there are shortcuts and you should consider those shortcuts in doing them, especially if this is multiple choice. But let's just say that this direction is going to be the negative direction and this direction will be the positive direction. That means I have 2 torques, the torque from the 30 Newton force and the torque from the 20 Newton force. And the 20 Newton force is the negative and the 30 Newton force is the positive. They both have the same torque arm length of 0.02 meters. But this one has a 30 Newton force, while this one has a 20 Newton force. But the angles are both 90 degrees. So I'm going to have positive 0.6 minus 0.4. And that's got to equal my net torque. So my net torque is going to be 0.2 meter newtons. But you'll probably get the answer wrong if you put in 0.2. They probably want negative 0.2 because I labeled mine in positive and negative, not using the traditional direction. But the traditional direction is into the page is negative and out of the page is positive. The net torque is into the page. So if you're going to use the traditional directions, then your answer probably has to be made to be negative. And that was just me not thinking ahead when I saw these. So if you put in 0.2, you probably got told to check your signs. Which, sorry, I know. The book does use the traditional convention for positive and negative on all of its answers. And into the page is considered negative for convention. Go ahead. I'm sorry, I could not hear you. No, the exam, if the exam's going to ask a question like this, they'll have something like this sitting on the page. If you see something like this on the page anywhere, like it'll be next to your diagram or something. They are identifying the directions that they are going to be calling positive. So they don't necessarily put positives next to them, but they're saying that all of these directions are considered positive. They might put the letter Z here to give you that. So they'll give you a I don't know, what word would you call this? A legend? You know, like a map legend? They will provide that if they have an expectation of your directions needing to match up with theirs. But that is, I mean, it's so unusual to see that I would not expect it. Now, the E&M exam, they'll do this more frequently, only because in the E&M exam, we have a lot more right-hand rule stuff to work out. So they will do that. But even them, I haven't seen one of these symbols in years on the tests. All right, so that's it for this question. So our next one was 7.
Oh, it was actually 9, right? This label.
It was 9. Okay, so that's still the next one. So question number 9.
I had a specific question on this. I kept trying to use the parallel axis theorem, like from the end of a bar.
For which one?
9.
Okay, I haven't gotten there yet. I don't even know what it looks like. Sorry, I am at the beck and call right now of mastering. Oh, and by the way, I have no idea when I'm supposed to release you guys to go to lunch. So I am sure one of you will be incredibly interested in making sure that happens. So if that's you, then you go. It says a 20 kilogram solid door is 220 centimeters tall and 95 centimeters wide. Don't be thrown off by this. The solid door is probably going to revolve about its natural hinges that are, you know, part of the problem. So a door is a bar, and you treat it just like a bar. Because it's rotating about its hinge, look straight down on it, and that's what you would suspect or that would be how you would treat it. So it's just gonna be the width of the door, not its height, unless it's, you know, moving about its height, but it's not. So it says 20 kilogram solid door is 95 centimeters wide. So that's what I'm going to use for L for the door. Does that make sense?
Yeah, that was my question.
Okay, I'm just making sure that we're good for that. It says, what is the door's moment of inertia for rotation on its hinges? So that's A. And since it's 20 kilograms, that's just 1/3 M L squared. Of course, you might have different numbers, but we use again, a bar about its end, assuming that's where it's rotating. And question B, what is the door's moment of inertia for rotation about a vertical axis inside the door, a distance D from one edge? Okay, so I assume that means that's D from one edge, like here. Is that how you guys interpret it? So we're still dealing with the 0.95, but now we're going to use the parallel axis theorem to get to this point. The height of the door still doesn't matter. And that's because we're still just dealing with how much the mass is away from this point. So I would do, we have this value, but I parallel is going to be equal, and I have to be careful here. This is I center of mass plus M X squared. So when you're calculating this, we have to either redo the moment of inertia from the center of the door, or you have to reevaluate D from the edge. You need to make a choice there though, because their value they're giving us is this for D. But the middle of the door is here. So when you're trying to figure out this moment of inertia, the parallel axis theorem is based on doing this from the middle of the door. So it's not hard to just put the 1/12 M L squared. But for this next part, you got to put this in terms of D. And we have D measured from the wrong place. So this is going to be what, half of the door minus D? And that's the shift you have to make. So 0.95 over 2 minus D is the actual shift. And now this becomes our new moment of inertia. So this problem, the emphasis is on recognition of where do you measure your shift from, center of mass, and you have to shift from knowing the moment of inertia at the center of mass. There are other ways to do this, but I don't know that I'm not sure it's useful to learn anything else besides just going back to the center of mass. So go ahead.
Why do you have to go back to the center of mass? Like, for some reason in my head, like
So you're asking why do we have to go back to the center of mass? It's been a long time since I've done the proof for the parallel axis theorem. So forgive me, but I don't know that I can give you a great explanation as to how the parallel axis theorem works, because I just haven't done it in such a long time. So probably if I reviewed that a little bit, I'd have a better explanation for you. But my recollection of when because I haven't done it in such a long time, I'd have to look back over it, and then I could probably answer your question better as to why do you have to go back to the center to do it. I think because I mean, what you have to do is for a smooth object is when you're working this out from the center of mass, you take like any shaped object and then you redo it with a shift inside your value for r plus the shift. And you get a bunch of these terms that you collect, and they all represent mx squared for the collection of those. But I don't quite remember why you had to start from the center of mass to be able to do it. So, and there's probably a way around doing what I did. Like you could probably have done that where we were on the edge was already a shift, right? So there's this was a shift to get the answer we had, right? That was question A, had us do it from the edge. And then the new question was from D. We probably could do this by, maybe subtracting these. That would cancel out the I center of mass and would give us an expression for our new one based on the old one. I'm not sure this is faster in any way, but it would do it. It would mean that we wouldn't have to go back to the center of mass to find our answer. So it would work, but again, is it easier? I don't know. I really don't. I mean, you're going to get this term that's going to cancel out, sure. But you're still going to have a cross term in there that you're going to have to deal with. So I don't know if that's easier or not. But try it. I mean, if you haven't done it yet, see if that works out faster. It might be a better way to do it. Because we know for a bar where the middle is and what its center of mass is, this would be the way to do it if you did not know what the moment of inertia to its center of mass was, which I could see them asking that on an exam. Why not? But I think that a lot of people would fail that question, including me, I think, if I probably just skip it and go on to the next one. So, am I good to go on to number 10? So, number 10. All right. So, number 10. This is number 9, number 10. All righty. Again, I'm thinking a problem like this, probably multiple choice. I haven't seen one like this on like on the FRQs ever. So, but they do stuff like this on the multiple choice. So I'm trying to make this look like an isosceles triangle. Is that isosceles enough for all of you? Is it okay? All right, so there's 3 balls, which I assume we can treat as point masses. One here, and one here, and one here. And these are each 100 grams, and this one is 200 grams. We're told this is 12 centimeters, and these are both 10 centimeters. And I suppose that we're probably going to be asked to find moment of inertia. If this were me and I was trying to tell you how I might do this on a FRQ, I would also want you to be able to find a few other points for the moment of inertia and the center of mass. So let's see what it asks. It says 3 masses shown in the figure are connected by those massless rods. Find the coordinates of the center of mass. Okay, good. That one's being asked. And find the coordinates of the center of mass. Find the x coordinate. Find the y coordinate. And find the moment of inertia about an axis through mass A. All right. Now, they didn't ask us to find the moment of inertia about the center of mass, which is too bad because that's probably more likely what you would see on an exam. Or finding the moment of inertia of like from this point. You know, that's not a bad idea either. These are the kinds of problems that I would expect. There has been a question on the FRQs where there's like an axis this way and this thing has been spun. So, or an axis this way and they spun it like that. So be prepared for questions like that. Those show up on the FRQs, but there's just some geometry here is all you have to worry about. But let's go ahead and find they want us to find the location of the center of mass. And we've not done it like this before. So I think this is a worthy activity. So for the first part of the problem, I'm going to put my y-axis here. And we're going to find the center of mass along the x direction. So what you might not know is that when you're finding the center of mass along the x direction, the y direction doesn't matter at all. So all you have to do is act like the 3 masses are here and do the problem. That's it. So I'm not going to leave it down there because it broke my triangle, but that means that I have 3 masses. So I have to just add up m times r, not r squared, for each of the masses and divide by the total mass. So the first mass is 100 and is located a distance 0 away from the edge. The next mass is 200 and is located 6 centimeters from the edge. I know that I'm doing these in not changing the units, but the units don't matter. It's going to give me an answer in centimeters, and that's okay. And the third one is 100 and it's located 12 centimeters away. Now, I'm pretty sure this is going to work out to have my X one right here in the middle because this is symmetrical. But just kind of proving it to you, take all of that. The total mass is 400. So when I work out the top, I get 6 times 200, that's 1200. And 12 times 100 is 1200. And then I have to divide by my total mass of 400, which when I work that out, that comes out to be 6 centimeters. So the X coordinate for the center of mass is 6 centimeters. Questions about that? All right, I do the same thing in the Y direction, meaning I can treat this mass like it's over here and this mass like it's over here and do the same thing in the Y direction. But to do that, I need to know this distance. So you need to do the trig. And my recollection is that this is a 6, 8, 10 triangle. So this is 8. Is that right? So now that I've done that, it's going to be all the same work. think we can just kind of, if you don't mind, use all of this over again. So I have 100 at 0 plus another 100 at 0 plus 200 at 8, all divided by 400. Again, it's symmetrical, so it's going to be in the middle. I got 1600 divided by 400, or 4 centimeters. So right there in the middle. Questions about that? Could you have done that without doing all the math? Probably. It was symmetrical. I had 200 grams at the bottom, 200 grams at the top. It's got to be in the middle. It was 100, 200, 100. It was symmetrical, so it's probably in the middle. So on a multiple choice, if you see some symmetry like this, you might be able to save some time. What you're probably going to be unable to do, though, is the moment of inertia without actually working it out. You'll probably have to work it out. And for the moment of inertia, they want the moment of inertia from here, which effectively wipes out the 200-gram mass. And the two 100-gram masses are the exact same distance away from mass A. So don't waste your time. You have to sum each of the masses and their distance away squared. Now for this one, you probably should put this all in in kilograms, newtons, meters, all that good stuff. But there's two of them. They both have the same mass, 0.1 kilograms, and they both are the same distance away, 0.1 squared. So don't spend a lot of time on that. It's going to be 0.01 times 0.1, that's 0.001. And times 2 makes it 0.002 kilogram meter squared. But you probably have to put it in terms of kilograms and meters. They didn't ask a particularly interesting question there. But is there another question? Yep. There's a part D. Find the moment of inertia about an axis that passes through masses B and C. The only axis that can pass through B and C is the x-axis. So that suggests that this thing is spinning about here. I assume that's what they mean. Is that what you guys think? So if that's the case, the two 100-gram masses suddenly do not contribute to the moment of inertia. And the only thing that does is the 200-gram mass, which is 8 centimeters away. So 0.2 times 0.08 squared. This is going to be the moment of inertia. I don't want to do that. Can you? I mean, you know what to do. You're just going to multiply with the calculator here. It's 0.0064 times 0.2. So I don't know. I don't know what it's going to be. Okay, 0.001. Yay. There you go. Not too terrible. These point mass calculations are pretty straightforward. So I don't want you to worry about them too much. They do show up on the multiple choice. They generally are triangles or squares. And so, they're not going to throw a hexagon at you or something like that with some weird angles. They're going to stick with something like this. Can you do the point masses? Can you not? The most they might do is the diagonal on the square or something like that. All right, so that leaves only one more. What was the other one? Was it 11? What's that? 15. I can hear that whistle blowing outside. That's definitely meaning that they are shooing all the people away from lunch. So that means lunch must be coming up for you guys. So number 15. A cylinder of radius r, length L, mass m, is released from rest on a slope inclined angle theta. It is oriented to roll straight down the slope. If the slope were frictionless, the cylinder would slide down the slope without rotating. What is the minimum coefficient of static friction needed for the cylinder to roll down the slope without slipping? You know how much I love this question, right? I really do. I really do. So we did this in class the other day, and not to put a finer point on it or not, but we got to figure out the size of that frictional force and then use it to find mu. There's no shortcuts here. I'm sure there might be shortcuts, but we're not going to take them. Does it say it's a hollow cylinder? A cylinder. Well, that means that a moment of inertia of 1/2 mr squared. And like I said, the pivot point is here. We should look at the torque. We know everything about the forces acting on it. I don't have to go back through that. We've got mg sine theta minus friction in the x direction. And we know that we know the normal force equals mg cosine theta. We're not getting away from that. We want to find out what mu is. So the minimum coefficient of static friction that's needed for the cylinder to roll down the slope. So I want to look at the torque. I want to look at the torque about this point and set it equal to I alpha. And I is going to be 1/2 mr squared plus mr squared, because we're going to shift it for the center of mass. I'm sorry, shift it for the axis that's here. And that's got to equal A over R. What torque does this? What torque does that is mg sine theta times R. Right? It's this torque. Like I said, we did this in class, so I don't feel too bad rushing through it. All that look familiar? The R's all cancel out. And we're going to get here mg sine theta equals, I believe this is 3/2 m times A. M's cancel out. I get g sine theta equals 3/2 A. Now you have a choice what you do next. To me, the choice that we do next is recognize that the friction is still part of this problem here, MA. We can solve for the friction, or we can solve for the friction about this point here like we did in class. If we do this one, the friction equals, R times the friction equals 1/2 mr squared times A over R. This doesn't let us get to mu though. We want the minimum mu. So how would we get to mu if we want the minimum mu? I think we're going to have to do this. Minimum mu is when this becomes an equal sign. That's minimum mu. So I think we bring those three things together. We know that A is going to be 2/3 g sine theta. F is going to be mu mg cosine theta. The R's cancel and I get 1/2 m 2/3 g sine theta. There, all of that. I did a lot there. I'm trying to rush to the end, but I use this for friction because we have to be at the max. And I put that here. I canceled out all the R's. And I put this for acceleration so that we get one relationship that has just mu and the angle in it. And M cancels out. G cancels out. 2 cancels out. And it looks like mu equals 1/3 tan theta. I went really fast there and I apologize. I should have gone slower. This was not the only way to do it. We could have used this and done it there too. It would have done the same thing. But we needed to get a relationship for friction to do this. So like I said, I went super fast, but I believe lunch is about to start for you guys any second. So I didn't want to screw up lunch for you guys. So that's that for today. My plan is simple. Tomorrow,